Imagine you're using your favorite text editor and just made a mistake. You instinctively press Ctrl-Z and the error disappears as if it never happened. But have you ever wondered how that undo action works? Do you know what's happening behind the scenes when you correct your mistake with a single keystroke? By the end of this video, you'll understand the practical applications of stacks. And having studied the complete lesson, you'll understand how stacks are used in 3 key areas: managing function calls in programming, converting expressions from infix to postfix, and implementing undo mechanisms in software. In Java, a stack is more than just a concept. It's a data structure implemented with its own dedicated class called stack. This means that when you create a stack in your Java program, you're essentially creating an object of this stack class. This stack object comes equipped with a set of methods specifically designed to manipulate data. At their core, stacks operate on this last in, first out, or LIFO principle. To understand LIFO, imagine a stack of plates at a buffet. When you stock up the plates, you add a new plate on top of the stack of plates. If you need to use a plate, you remove the top plate first. The plate at the bottom stays there until all the plates above it are removed. Stacks work precisely like that. You push data onto the stack, and when you need to retrieve it, you pop the most recent data off first. This behavior makes stacks incredibly useful in scenarios where you must keep track of actions or tasks in a specific order and revisit them in reverse. But how does this abstract concept of stacks translate into something practical in the programming world? Let's explore one of the most fundamental areas where stacks play a critical role in function calls. Have you ever wondered how a computer knows where to return after calling a function? Here's where stacks come into play. When a function is called, the code's current position and local variables are pushed onto the stack. The function then executes, and once it's done, the program pops the return address off the stack and jumps back to where it left off. This process ensures that the program can handle multiple nested function calls and return to the correct point in the code each time. Without stacks, keeping track of these return points would be chaotic and error-prone. The initial call is add 3 and 2. The stack starts with add 3 and 2 as the top and only element. The first recursive call is add 4 and 1. Therefore, add 4 and 1 is now pushed onto the stack, becoming the new top element. Add 3 and 2 remains just below it. The second recursive call is add 5 and 0. Add 5 and 0 is pushed onto the stack, becoming the new top element. The previous top, add 4 and 1, is now just below it. Returning from recursive calls, as add 5 and 0 hits the base case y equals 0, it returns a value, and the stack begins to unwind. Add 5 and 0 is popped off, making add 4 and 1 the top element again, followed by add 3 and 2 as the stack continues to unwind. Next, let's talk about expression evaluation, particularly converting infix expressions. For instance, 3 plus 4 multiplied by 5 to a postfix notation like 3, 4, 5 multiplied sign, addition, sign. This might sound complex, but it's a critical process in how computers evaluate mathematical expressions. In infix notation, operators are placed between operands, which can lead to ambiguity in the order of operations. To simplify this for computation, the expression is converted to postfix notation, where the operators follow the operands. Stacks are the perfect tool for this conversion because they allow us to temporarily store operators and ensure they are applied in the correct order. By pushing and popping operators at the right moments, the stack helps us rearrange the expression into a form that's easy for computers to evaluate. Starting with the infix expression, 3 plus 4 multiplied by 5, where operators are placed between operands. Operator precedence can complicate the evaluation, so converting to postfix notation simplifies it. Now, Let's take a look at this conversion, step by step. First, the operand 3 is encountered and goes directly into postfix expression. Next, the plus operator appears. Since the stack is empty, plus is pushed onto the stack. The next operand 4 is added directly to the postfix expression. Now, the multiply operator is encountered. With higher precedence than plus, multiply is pushed onto the stack above plus. The final operand, 5, is then added to the postfix expression. With no more operands left, the stack proves its usefulness. Operators are popped in the correct order. First, multiply, then plus, ensuring the postfix expression is properly formed. The final postfix notation is 3, 4, 5 multiply plus. Thanks to the stack, the operations are organized in the correct sequence without needing to consider precedence directly. That's how the stack makes converting infix to postfix easy. It uses its LIFO order to automatically figure out the right order for math operations. Finally, let's understand stacks through the undo mechanism mentioned earlier. Whether in a video game, text editor, or other software, the ability to undo actions relies heavily on stacks. Every time you act, the software pushes a record of that action onto a stack. If you decide to undo the action, the software simply pops the most recent action off the stack and reverses it. Stacks are ideal for managing a history of actions because of their LIFO nature, allowing you to backtrack step by step. Actions are added to the stack from the bottom up, with each new action placed on top. During an undo, actions are removed from the top down in reverse order. Stacks are everywhere, from the books in the library to the software we use daily. By understanding how they work and recognizing their use cases, you can see the power of this simple yet effective data structure. Whether you're managing tasks, navigating through web pages, or coding, stacks provide an organized way to handle data and operations efficiently. Embrace this concept, and you'll find yourself better equipped to tackle various challenges in both programming and everyday life.